Welcome to the Sleepless Universe. In this video, we'll embark on a journey to some of the most fascinating yet instantly lethal places in the cosmos. Drop a comment to let me know where you're watching from. If you enjoy this kind of content, I'd truly appreciate a like and a subscription. Now, sit back, relax, and enjoy the ride. The event horizon of a black hole. Imagine drifting in the quiet dark where stars look like frost on glass, and the Milky Way is a pale river across the night. Ahead, there is a circle that refuses to shine, a hole punched out of starlight. Around it, matter screams without a voice, a whirlpool of incandescent plasma whipping so fast that day and night become meaningless. You are approaching the event horizon of a stellar mass black hole, a boundary that is not a surface and not a wall, but a point of no return in space-time itself. Nothing on your suit rips or hisses. There is no warning alarm designed for this. The universe simply changes the rules underneath your feet. Long before you touch that boundary, the environment is trying to end you in several competing ways. The accretion disk is a forge where atoms rub together at a significant fraction of the speed of light and convert their motion into radiation. X-rays and gamma rays pelt your body. Each photon is a tiny hammer with the energy to smash molecular bonds. Your visor darkens to protect your eyes, but shielding that would stop a hospital X-ray is useless here. The field is not a flash. It is a flood. Cells do not fail gracefully. DNA strands break in clusters. Proteins misfold. The clean choreography of cellular repair stalls and then collapses. You do not feel pain from this specifically, at least not in a way that nerves can interpret, but the damage is immediate and compounding. Between you and the dark core, the gravity gradient sharpens like the edge of a blade. The name spaghettification sounds cartoonish, but the physics is exact. Gravity is stronger on your feet than on your head, by enough to matter. And the difference grows exponentially as you close distance. Tidal forces are a sculptor with a cruel style. Your body, which is used to uniform fields, begins to stretch along the direction of fall and compress from the sides. Ligaments tauten, blood pulls. The fluid that cushions your spine now works against it. Bones do not snap all at once. They complain in microfractures as the skeleton tries to keep a shape space-time no longer favors. The process is silent and methodical, like a press closing on soft metal. Light behaves strangely here. Photons that leave the accretion disk on paths nearly tangent to the hole can loop around and come from directions that defy intuition. Behind you, in your visor reflection, you see a smeared halo that is both the front and the back of the disk at once. The closer you get, the more the sky warps into a luminous ring, and the black center swallows not only stars, but also the geometry that used to make sense. This is not an optical trick caused by glass or atmosphere. It is curvature. Space tells light how to travel, and the black hole has written a roadmap of spirals and traps. Time is no longer a single shared rhythm. To a distant observer with a telescope, your descent is slowing, your signals red-shifting, your last wave stretched into a low murmur, and then into nothing. They would say you never quite crossed the horizon. You taper toward it asymptotically, turning into a frozen ember. From your perspective, their clock is what slows, galaxies cooling into a deep, tintless hush as your own seconds remain normal. This disagreement is not a philosophical point. It defines how death arrives. For you, events happen in a sequence you can count, and the horizon is a place you reach. For them, it is a photograph that never completes its final exposure. If the black hole spins, and most do, space-time itself is dragged around with it. You do not need to touch the horizon to feel this frame dragging. Your trajectory bends, not because of a wind, but because the ruler and the stopwatch you would use to define straight lines and equal intervals twist in your hands. The region outside the horizon, where this twisting becomes inescapable, has a name borrowed from myth, the ergosphere. Within it, orbits are not optional, and rotational energy can be mined by clever processes, but none of that helps a human falling without a spacecraft. The twisting creates shear that adds to your torment, complicating the tidal field with sideways strains that your joints are not built to accommodate. Near the photon sphere, where light can orbit like a bead on a wire, the radiation pressure clatters against you. Your suit, A miracle of engineering for vacuum and cold and micrometeoroids was not rated for this furnace. Its outer layers begin to ablate, not in flames that need oxygen, but in sublimation from energy density alone. The fabric peels at the molecular level. You have redundant cooling loops, ice packs, phase change materials meant for sunlit lunar days and Martian noon, and they flash through their capacity in moments. Heat does not conduct through vacuum. It batters you through photons and particles, through ion storms that crawl through electronics and flip bits like a mischievous child. Your life support computer throws errors that no training sim included. The last clean numbers on your wrist are wrong by the time you read them. The strangest thing is how ordinary your thoughts remain for a while. You inventory the sensations like a checklist, because a human brain is built to narrate even as it fails. Your vestibular system is lost, not because there is no up, but because up is being redrafted faster than it can compensate. Your balance says you are falling forward, then inward, then nowhere. The stars are a ring. The ring widens and narrows as if the sky were breathing. The hole grows until it is not a hole, but your entire environment. The concept of a round. And even fear has trouble finding a foothold when there is no longer a clear direction to run. If you had approached a supermassive black hole instead of this compact stellar remnant, the story would differ in an important way. For the truly gigantic ones, the gravity gradient at the horizon can be gentle enough that your body would survive the crossing without immediate tidal disassembly, only to be crushed deeper inside. Here, with a smaller mass and a sharper curvature, nature is not patient. The point of no return and the point of structural failure are close neighbors. Your spine is the first to learn that lesson. Vertebrae are marvelous compromises between stiffness and flexibility. They are also levers. The tides can pry. Discs bulge and tear. Nerves complain and then go quiet as pressure on the cord interrupts their signals. A blackout in the wiring harness of the self. Radiation has not forgotten you. Secondary particles bloom around you when high-energy photons strike the scant matter in your suit and body. It is a personal storm, a cloud chamber where each track ends in chemistry broken beyond repair. In a medical context, we talk about dose, about thresholds beyond which a body cannot recover. Here, the language of dose is comic understatement. Your bone marrow, which quietly feeds your bloodstream, a constant supply of resilient new cells, is being methodically destroyed. The gut lining, a surface area the size of a small apartment folded into you, sloughs under the insult of ionizing energy. These are causes of death measured in hours to days in a hospital ward. You do not have hours. Gravity insists on minutes. You try to look away from the hole and search for something familiar, and even that gesture is captured. Every ray of light you see from the wider universe is climbing out of a gravitational well to reach your eyes. Blues and reds are recalculated, apparent brightness reshuffled. The cosmic microwave background, that soft afterglow of the early universe, would look hotter, its wavelength squeezed by your descent, a ghostly fever that does not respect suits or skin. It is a reminder that nothing in physics happens in isolation. Even the most distant light is part of the local story, when space-time is this bent. The horizon is not a surface you can hit. There is no splash and no thud. There is only a line in the geometry that your path crosses, the place where all future paths lead inward. If your suit survived the tidal field to this point, if by some contrivance of approach vector and black hole mass and accidental shielding, you made it here mostly intact, the experience would be infamous for its lack of drama. No instrument in your hand would spike. No crack would race across your visor. Yet, meaning changes here. Messages you send cannot climb out. Your flashlight, a beam that has always been loyal to your direction, now paints a future you cannot share with anyone outside. Inside the horizon, the inward fall is not a motion you can stop with rockets or effort. It is an analog of time itself. Asking to turn around is like asking yesterday to return. The shape your death takes now is set by mathematics, written when massive stars ran out of ways to support their own weight. The singularity is not a point in space so much as a destination in time. It lies ahead of you, the way tomorrow lies ahead of today. Tidal forces continue to climb. Each factor of 2 in distance shrinks the scales on which the gradient acts until molecules, atoms, even nuclei face a lever bigger than their bonds. You will not notice the hierarchy of this disassembly. Consciousness is not built to narrate its own erasure past certain accelerations and pains, and with the spine compromised and the brain awash in broken chemistry, awareness narrows to a thin, flickering channel and then snips. There is a stray thought that might have visited you earlier and returns now with a bitter smile. From the outside, the accretion disk can launch jets along the hole's poles that stab thousands of light years into interstellar space. Bright lances of radio and X-ray light, powered by magnetic fields in rotation. They are beautiful and ruthless, star formation's midwives and executioners, able to carve cavities in galaxies and starve regions of fresh gas. All that grandeur is fed by things like you, by matter earning its last flashes of brightness before the ledger closes. You are both spectacle and fuel in a universe that wastes nothing. In your final seconds of functioning perception, gravity does an odd favor. It accelerates your time relative to the outside so fiercely that external change runs fast on your personal clock. The disk's flickers blur, the ring of light smooths. The last photons you will ever see arrive from directions that used to be mutually exclusive. Your world simplifies into symmetry, a halo, and a darkness with you balanced between. And then even that balance dissolves under numbers you could have written but never felt until now. There is no peace here, but there is an end, and it is absolute. Inside the event horizon, the rules that held your life together outside have already been abandoned. Up to this point, you could still frame your fall in the language of travel. A location to leave, a location to reach. Now, even those words are mismatched to reality. There is no where to go back to, no when to aim for. All paths lead deeper, not because the space is tight, but because the future itself has been rewritten to aim inward. You are a bead on the world's strangest one-way track. The gravitational gradient, already extreme before you crossed, is now beyond the capacity of any biological or mechanical structure to resist. The difference in pull between one end of your body and the other grows so violently that even the most resilient materials known to science would be torn into molecular filaments. To outside observers, if they could somehow follow your path beyond the horizon, the concept of you as a single object would already be gone. Inside, there is no resistance left to give. What remains of your body's structure is stretched thinner than a strand of DNA and then dispersed into an atomic drizzle. But even this is not the ultimate limit. The deeper you fall, the smaller the sphere in which you can exist before the next order of physics takes hold. Tidal forces stop acting on molecules and start acting on the quarks inside protons and neutrons, the very building blocks of matter. The mathematical description here is so violent, it almost feels like a metaphor, but it is exact. The curvature of space-time at these scales exceeds anything else in the known universe. If the laws of physics as we know them still hold, you are being funneled toward a singularity, a place of infinite density and zero volume, where our equations stop making sense. For you, there is no moment of impact. There is no sensation of hitting a wall or floor, because the singularity is not a place in the ordinary sense. It is a time, a final tick on a clock that only you can read. In the last instant, the concept of distance becomes meaningless. All points become one point. All directions collapse into a single outcome. Whatever was left of your awareness, your body, or the information that once described you is consumed by the geometry itself. The universe reclaims the matter that was once you and folds it into its most secret ledger. Outside, your death happened long ago. Or, in a way, it never happened at all. Light from your final approach might still be en route to distant observers centuries later. The slow-motion red ghost of your fall continuing to stretch and fade. The black hole will not advertise your addition to its mass in any obvious way. There will be no ripple in the disk to mark the occasion, no flare for astronomers to record. You are part of it now, your mass indistinguishable from the billions of tons that came before you. Your history erased except for the effect of your weight on the hole's future behavior. And this is perhaps the strangest part. The black hole is not empty. It is full of the past, every faller, every scrap of gas, every fragment of star and planet that crossed the horizon since its birth. But from the outside, all of that history is crushed into a single featureless shape, described by only three properties: mass, spin, and electric charge. The details of who or what you were are not merely hidden, they are gone. This is the so-called no-hair theorem in action. The black hole does not keep a diary. In the great ledger of cosmic danger, the event horizon is a paradoxical entry. It is not an explosion, not a fire, not a cold that freezes, and yet it is one of the most absolute ends you can encounter. It kills not only the body, but the possibility of recovery, and perhaps even the possibility of memory. Death here is not a drama. It is a mathematical inevitability, one that feels impersonal precisely because it is so perfect. If there is any consolation, it is this: for all the horror and finality, your fall is part of the machinery that shapes galaxies. Black holes are not only destroyers, they are architects, influencing the motion of stars, seeding the structures we see across the universe. The light from matter's last moments of freedom near the horizon becomes a beacon for telescopes across time, telling a story that outlasts you by eons. You die here, but the consequences of your death ripple outward, written in the dance of galaxies and the glow of X-ray skies. And so, if the event horizon of a black hole is to claim you, it does so not with malice, but with an indifferent precision that belongs entirely to the fabric of space-time. You are unmade at every level: physical, informational, temporal. And in the process, you become part of one of the most mysterious and influential objects in the universe: the surface of Io, Jupiter's volcanic moon. Far from the warmth of the sun, past the familiar shapes of Mars and Jupiter's vast storms, hangs a small, mottled sphere that seems almost benign at first glance. Its surface is dappled in yellows, oranges, and reds, like some frozen autumn leaf. But this is Io, Jupiter's innermost large moon, and the most volcanically active body in the solar system. What looks like a strange mosaic from afar is actually a constantly shifting, tortured crust of sulfur and basalt, torn open and remade by forces so immense that standing here would end you in moments. The first thing to understand about Io is that it is locked in a brutal gravitational relationship. It orbits Jupiter in just under 2 days, but it is not alone. The neighboring moons Europa and Ganymede keep tugging it into a slightly eccentric orbit, forcing Io to stretch and flex in Jupiter's colossal gravity field. This flexing is not gentle. It needs the moon's interior the way hands might need dough, except the hands are planet-sized and the dough is rock. Friction from this constant stretching heats Io's interior until parts of it are molten. Not just warm, but seething. That heat has to escape somewhere, and it does so explosively. On the surface, that energy reveals itself in towering volcanic plumes. These aren't the glowing red fountains of Hawaii or Iceland. They are supersonic geysers of molten sulfur and silicate rock, blasted hundreds of kilometers into space. The plume from the volcano Pele, for example, can rise so high it forms a faint umbrella-shaped cloud, visible from passing spacecraft. If you were somehow standing near the vent when one of these eruptions began, you wouldn't have time to register the sight before it killed you. The shockwave alone, even in Io's thin atmosphere, would throw you off your feet, tearing at your suit with sharp sulfur-rich particles that behave like microscopic shrapnel. And the heat is not something your body can bargain with. Near an active vent, the temperature can spike above 1,600 degrees Celsius. That's hotter than the surface of Venus, hotter than molten steel. Your suit's thermal protection would fail almost instantly. The polymers and composites would soften and then vaporize. Even if you somehow avoided the direct blast, the radiant heat alone would cook you in seconds, searing lungs and eyes long before your brain could process a full thought. But Io's danger doesn't stop at the volcanoes themselves. The moon sits deep inside Jupiter's magnetosphere, a magnetic bubble so vast it stretches millions of kilometers into space. Jupiter's rapid rotation and intense magnetic field trap, streams of high-energy particles from the solar wind, and from Io's own volcanic gases, turning the space around the moon into a radiation oven. Here, the dosage is measured not in hours or minutes, but in seconds. Without shielding thicker than a bank vault's walls, your DNA would be shredded before you could take a second breath. The irony is that the same eruptions that make Io visually stunning also load the surrounding space with lethal plasma, feeding Jupiter's glowing auroras and painting invisible death across the sky. Walking across Io would be like moving through a minefield where every step risks breaching a crust only meters thick above pockets of molten rock. The ground here is unstable, a crust of sulfur frost over a boiling, roiling mantle. You might plant a foot on what looks like solid ground only for it to collapse, dropping you into a fissure that belches superheated gas and molten sulfur. There is no rescue from that. Even if a ship hovered nearby, there would be no time to reel you back up before the fumes and heat overwhelmed you. The air, if you can call it that, offers no comfort. Io's atmosphere is a whisper-thin layer of sulfur dioxide gas. You couldn't breathe it, but even if you could, it would freeze in your lungs when the volcanic heat isn't actively baking you alive. And those swings are violent. A night on Io can plunge to minus 160 degrees Celsius, cold enough to turn exposed skin brittle before it burns in the next eruption's glow. The rapid shifts between cryogenic cold and furnace heat would make every material in your suit and equipment expand and contract repeatedly, hastening their failure. Even from orbit, Io's surface is in constant motion. New lava flows paint the landscape in black and red streaks. Old features vanish under blankets of sulfur frost that fall like snow from the plumes, only to be vaporized days or weeks later by another eruption. If you tried to chart a safe route on foot, your map would be obsolete before you finished drawing it. This is not a place where terrain is reliable. It is alive in a way that is hostile to human life. And still, there is a beauty here that tempts curiosity. Against the black backdrop of space, Io's volcanic plumes catch sunlight in ghostly arcs, creating halos of ice crystals and sulfur dust. From the right angle, Jupiter itself looms enormous in the sky, its banded clouds and swirling storms dominating the horizon. But that beauty is indifferent to your survival. The planet's magnetic field continues to pump radiation into your cells. The surface beneath you shifts and breathes. And somewhere out of sight, pressure is building toward the next eruption. If by some impossible stroke of luck you avoided direct exposure to a vent or fissure, you would still be living on borrowed time. The radiation dose here is strong enough to cause acute radiation sickness almost immediately. Nausea, confusion, a burning sensation in the skin. Within minutes, your central nervous system would begin to fail. The combination of heat, cold, instability underfoot, and the invisible rain of charged particles makes Io a place that does not merely resist life, it repels it. What makes Io's lethality fascinating is that it doesn't rely on one single factor. It's not just the heat or the radiation or the instability of the ground. It is all of them working together, an environment designed by cosmic mechanics to be unlivable in every conceivable way. Each hazard feeds another. Tidal heating drives the volcanoes, which feed the radiation belts, which make rescue nearly impossible. In this way, Io becomes more than a moon. It is a perfect storm of planetary violence, a reminder that beauty and danger often share the same face in our universe. The deeper you remain within Io's grasp, the more the moon's layered dangers close in from every direction. Radiation, unlike a plume or a lava flow, does not give you a warning that you can see or hear. The charged particles streaming from Jupiter's magnetosphere arrive invisibly, moving at nearly the speed of light. Inside your body, they tear through tissue like microscopic bullets, snapping chemical bonds and DNA, disrupting the electrical signals and nerves, and triggering cascades of molecular damage your cells have no time to repair. In a place like Io, the dose is so high that even the best medical technology we have on Earth could not reverse the damage once it begins. The volcanic hazards are no less relentless. Io's surface is pockmarked with calderas, immense volcanic depressions, some larger than entire states back home. From orbit, they look dormant, but many of them are only hours or days away from their next eruption. Pressure builds silently below as sulfur and silicate magma churn in subterranean chambers. Then, without much warning, the crust fractures, releasing geysers of molten material at speeds that can exceed Mach 1. These eruptions eject not just liquid rock, but also clouds of ash and dust that can stay aloft in Io's feeble gravity for hours, traveling hundreds of kilometers before settling. That ash is no ordinary volcanic dust. It's composed of sharp, glass-like particles of silicate and tiny crystals of sulfur compounds. Inhaling even a small amount without filtration would shred lung tissue. On the surface of Io, such ash would coat your visor and instruments, abrading seals and joints. Your suit's mobility systems, already stressed by extreme temperatures, would grind under the intrusion of fine, abrasive particles. Eventually, the smallest breach in your protective layers would allow the vacuum and chemical hostility of Io's atmosphere to pour in, and there would be no second chance to seal it. The temperature swings here are some of the most extreme in the solar system. During Io's brief day, surfaces near active flows can be hotter than molten steel. During the night, frost made of sulfur dioxide settles in layers across the landscape, solidifying into a brittle crust. Step on such frost in the cold, and it will crunch underfoot. Step on it minutes later after an eruption, and it might vaporize into choking clouds before you can take a second step. The instability of these transitions means that equipment calibrated for a constant environment simply cannot survive. Seals warp, metals fatigue, and electronics glitch in ways that would seem almost random if you didn't understand the violent thermal cycling causing them. Even the ground beneath you can betray you without warning. Io's crust is thin in many regions, a hardened skin over molten reservoirs. A fissure might open beneath you without an audible crack. The reduced gravity here makes seismic signals behave differently, less of a jolt and more of a rolling lurch. One moment, you are standing on an uneven, frozen plain of sulfur frost. The next, you are sinking into a widening vent, spewing a mixture of toxic gas and incandescent rock. At those temperatures, your suit and body are consumed together, vaporized before rescue could even reach the coordinates of your fall. If you somehow avoided these surface hazards, you would still have to contend with Io's position inside Jupiter's radiation belts. These belts are intensified by the constant feed of material from Io's own eruptions, which eject hundreds of kilograms of gas and dust every second into Jupiter's magnetosphere. This material becomes ionized and trapped, creating an even denser, more lethal plasma environment. It's an irony almost too perfect. Io's own volcanic fury not only makes its surface deadly, but also poisons the very space around it. Any ship attempting a low orbit for extraction would be subjected to intense radiation bombardment, forcing it to keep its time near the moon to mere minutes. That means if you're stranded, help can't linger, and it likely can't reach you at all. From a purely scientific standpoint, Io is a treasure. It is a living laboratory of planetary geology, a world where processes we only theorize about on Earth unfold openly and violently every day. But for a human body, it is unmitigated hostility. Every system we rely on, respiration, circulation, neural signaling, is under simultaneous attack. There is no acclimatization, no slow adaptation. The moon offers only one form of mercy. Death here is swift. Whether by radiation, heat, toxic atmosphere, or structural collapse beneath your feet, the chain of events leading to your end moves far faster than your survival instincts can adapt to. And yet, there's a strange poetry to Io's role in the cosmos. The very forces that make it lethal are the same forces that light up Jupiter's auroras in ribbons of electric blue and purple. Its constant eruptions replenish the gas torus, a donut-shaped cloud of plasma that encircles Jupiter, creating a spectacle that can be seen with the right instruments from millions of kilometers away. Io is both victim and artist, dying and creating in the same act, reshaping itself endlessly in the grip of its massive parent planet. To visit Io, even briefly, would be to step into a dance of destruction and renewal that no human technology is yet ready to face. It is a place that burns its history into the sky and the magnetosphere, writing its legacy in both light and radiation. And for anyone unlucky enough to stand on its restless crust, that legacy would include their final, irreversible moments. The boiling atmosphere of Venus. Imagine standing on a world where the horizon shimmers not with heat haze, but with the distortion of an atmosphere so dense it feels more like an ocean than a sky. This is Venus, Earth's so-called twin in size and mass, Yet in every other respect, its mirror image in hostility. From orbit, its creamy yellow clouds look serene, even soft, but beneath them lies an environment so extreme that death here is not just inevitable, it's instant and multifaceted. Venus is a planet that has turned itself inside out over eons, wrapping its surface in a suffocating, superheated blanket of carbon dioxide and sulfuric acid. At ground level, the atmospheric pressure is about 90 times greater than Earth's, equivalent to being nearly a kilometer underwater. Before the heat even reaches you, this pressure alone is enough to crush human lungs and deform unreinforced equipment. Your body is not designed for such weight. The delicate alveoli in your lungs would collapse like paper under a steamroller. Without a pressure suit rated for deep ocean depths, your chest simply couldn't expand to draw in breath, even if the air were breathable, which it isn't. And then there's the heat. The surface temperature of Venus hovers around 465 degrees Celsius, hotter than the surface of Mercury, despite being nearly twice as far from the sun. This heat is not a passing wave you could avoid by seeking shade. It's the planet's default state, the result of an unrelenting greenhouse effect, where sunlight passes through the thick atmosphere, warms the surface, and the resulting infrared radiation is trapped and multiplied by the dense CO2. Every rock, every grain of dust radiates this heat back at you. The air is so hot, it would flash fry any organic material instantly, boiling moisture out of skin and eyes in a heartbeat. Metals like lead or zinc. Here, they melt into puddles. Even if your suit could resist the crushing pressure and furnace heat for a time, Venus has another layer of cruelty. Its clouds. 40 to 60 kilometers above the surface, thick layers of sulfuric acid drift in vast, turbulent formations. These clouds don't stay politely aloft. Particles and droplets settle downward, mingling with the already toxic air. Acid is a patient killer compared to heat and pressure, but here it acts quickly, eating through most protective coatings and corroding electronics. In the upper atmosphere, this acid exists as a persistent drizzle. On the surface, microscopic acid particles still hang in the air, ready to pit and weaken anything exposed. But it's not just the chemical makeup of the atmosphere that's dangerous. The density of the air makes it a conductor of heat and sound far better than Earth's. If you were somehow shielded from the temperature, you would still feel the constant press of air molecules against you, conducting heat into your body far faster than any terrestrial environment. And while sound would travel well, it would be warped, slowed and thickened by the pressure. A voice, if it could survive transmission here, would sound deep, muffled, and alien. The light on Venus is another unsettling factor. While the sun does shine here, it's filtered through so much atmosphere and cloud that the sky glows a dim, yellowish orange. There are no blue skies, no stars visible, only a perpetual, heavy daylight that feels more like a furnace room than a planet. Shadows are faint and blurred because the thick air scatters light in all directions. This scattering is not the gentle blue haze of Earth's sky. It is oppressive, bathing the landscape in an unchanging monotone that offers no relief for the eyes. If you imagine standing still for just a moment, every hazard on Venus begins to act at once. The pressure pushes on every surface of your body with the weight of a building. The heat seeps relentlessly through your suit, challenging its cooling systems to keep up. The air you cannot breathe presses against your visor, its toxic chemistry waiting for the smallest breach. Even the ground beneath you is part of the threat. Venus's surface is shaped by volcanic plains, fractured ridges, and impact craters softened by eons of erosion, not by water, but by the atmosphere itself, which can deform rock over geological timescales. The rocks you see are baked and baked again, their edges dulled, their surfaces coated in mineral films deposited by the slow cooking of the crust. And yet, there's no wind here to sweep you away into safety or danger. At the surface, the air moves sluggishly, centimeters per second, because its density means even a gentle push carries enormous force. Higher in the atmosphere, winds race at hurricane speeds, but by the time they reach ground level, they've been damped into a slow, suffocating crawl. This deceptive calm means you won't hear the kind of roaring storm that signals danger. The air simply sits, heavy and lethal, until you succumb. If your suit failed for any reason, a crack in the visor, a joint seal giving way, a cooling system overload, death would be swift and layered. The first sensation would be the crushing weight of the air itself. Your eardrums would rupture, your chest would lock, and before you could even gasp, the heat would begin to destroy tissue. Moisture on your skin and in your eyes would boil away in seconds, leaving behind burns from both temperature and chemical corrosion. There's no fainting and waking here. The cascade of system failures in your body would be terminal within moments. The strangest part of Venus's lethality is that it comes wrapped in a deceptive appearance. Seen from space, the planet's thick clouds reflect sunlight beautifully, making Venus one of the brightest objects in Earth's night sky. Ancient cultures mistook it for a star, a beacon of beauty that inspired myth and poetry. But this beauty is a disguise. Under the clouds lies an unbroken record of planetary ruin, a surface so hostile that even our most robust robotic probes survive for only a couple of hours before succumbing to the combined assault of pressure, heat, and chemistry. And here's the final cruelty. Venus could have been a paradise. Models of its early history suggest it may once have had oceans, temperate climates, and a stable atmosphere not unlike Earth's. But something, perhaps a runaway greenhouse effect triggered by volcanic outgassing, tipped it into a spiral from which it could never recover. Now, it serves as both a warning and a marvel, a reminder of how quickly planetary conditions can change, and an example of nature's ability to craft an environment perfectly tuned to repel life. If by some miraculous technology you were able to survive the first minutes on Venus, the psychological impact of the place would begin to weigh on you almost as much as the physical dangers. There is no horizon of hope here, no distant mountains, no cooling breeze, no shifting weather to break the monotony. The sky remains the same yellow-orange glare, the air the same oppressive wall of heat and poison. Even the sounds you might expect from such an alien environment are muted. The density of the air damps high frequencies, making the world feel strangely muffled, as though you were listening to it through a thick wall. This constant sensory oppression would erode focus, reaction time, and morale. The ground beneath your boots, if your boots could withstand it, would not behave like Earth's familiar soil or stone. Much of Venus's surface is a vast expanse of basaltic rock, smoothed and reshaped by ancient lava flows. Some regions are fractured into tessera terrain, where ridges and valleys crisscross in patterns formed by intense tectonic compression. The footing would be uneven, and any movement would strain your suit's cooling systems as much as standing still. You'd also have to contend with the planet's deceptive gravity. At 90% of Earth's, it wouldn't feel drastically different at first, but the combination of that gravity with the crushing atmosphere means each step would be like walking under a heavy load, the pressure pushing against your body with every move. Venus is also a master of hiding its deadliest effects in plain sight. The air's opacity to infrared radiation means heat doesn't just come from the ground or direct sunlight. It radiates toward you from every direction. The sky itself is a source of heat here. Even if you stood in the shadow of a rock or probe, you'd feel the same blistering temperature because the air's molecules themselves are hot and constantly colliding, transferring energy into your suit and your body. Cooling systems would be in a constant state of overload, and once their energy reserves were exhausted, survival time would be measured in seconds. And then there's the chemistry of the place. The thick atmosphere is almost entirely carbon dioxide, with nitrogen as a distant second and trace amounts of sulfur dioxide. This sulfur dioxide, in combination with the planet's temperatures, can form corrosive compounds that attack even high-grade metals. The surface is thought to have deposits of metallic frost, not snow, but condensates of lead sulfide or bismuth sulfide that precipitate out in the cooler highland regions. These metallic coatings are a reminder that here, even the mountains are dressed in the products of a toxic sky. Touching or disturbing such material would coat equipment in a layer that could interfere with heat transfer, further stressing already overburdened systems. If you were here during one of Venus's seismic events, and the planet does experience quakes, the risks would multiply. The surface is under constant geological stress, with vast volcanic plains hinting at a history of catastrophic resurfacing events. A quake here could dislodge rockfalls or open fissures, not with the dramatic collapse you'd see on Earth, but with slow, pressurized movement. A crack might release superheated gas trapped beneath the crust, adding another invisible, lethal hazard to an environment already brimming with them. The clouds above are both distant and close in their effects. Though they hover high above the surface, the sulfuric acid droplets they carry are part of a planet-wide circulation that eventually brings their corrosive influence down to the ground. Electronics here face a constant battle against this chemical assault. Insulation breaks down, sensors become unreliable, and delicate connections corrode to the point of failure. For human survival, this means that life support readouts could become inaccurate without warning. A fatal risk in a place where every measurement matters. Even robotic missions, which don't have to contend with biology, meet their limits here. The Soviet Venera landers, some of the toughest probes ever built, were designed to survive for about an hour under Venusian conditions. They carried pressure hulls like miniature submarines and active cooling systems, yet most failed after 50 to 60 minutes. Their electronics fried, their hulls overheated, and their instruments either jammed or warped. For a human with far more delicate systems, that hour would be an impossible luxury without extraordinary protection. And the irony is that survival in the upper atmosphere of Venus is far easier. At an altitude of about 50 kilometers, the pressure and temperature are surprisingly Earth-like. Some scientists have even speculated about the possibility of floating habitats in these layers, riding on the relatively mild winds above the death zone below. But on the surface, there is no such reprieve. The only wind you'd feel would be the slow, heavy push of the air itself, moving too sluggishly to disperse heat or provide relief, yet dense enough to transfer its crushing weight into every part of you. If you did somehow linger here, the slow cumulative effects of the environment would catch you even before the catastrophic ones. The extreme heat would dehydrate you at a rate no hydration system could match, drawing water out of your body with every breath you took inside a failing suit. Your cardiovascular system would strain to push blood through vessels already dilating in response to the heat. Confusion, dizziness, and hallucinations would follow quickly. Your brain starved for proper thermal regulation and oxygen, even if your suit's oxygen supply remained intact. Venus is a planet without a single point of mercy. Every element of its environment, the crushing atmosphere, the intense heat, the toxic chemistry, the geological instability, works together in a layered assault. Death here is not a single dramatic blow, but a coordinated attack from all sides, leaving no path to escape. It is a reminder that not all hostile worlds are icy wastelands or explosive infernos. Some are smothering furnaces that kill not with speed alone, but with completeness. And yet, despite its hostility, Venus draws us back in our imagination. We wonder what it might have been before the runaway greenhouse took hold. We speculate about terraforming, about engineering a way to strip its atmosphere or shield it from the sun. But for now, the surface remains a place where human presence lasts only as long as our machines can endure. And those machines last minutes. Here, survival is not an achievement, it is a countdown. A neutron star's magnetosphere. Imagine a place where gravity crushes matter into forms so dense that a teaspoon of it would outweigh a mountain, and where magnetic fields are so strong they could tear electrons away from atoms across thousands of kilometers. This is the realm of a neutron star, the collapsed core of a massive star that has exploded as a supernova. If the event horizon of a black hole is a silent point of no return, then a neutron star's magnetosphere is a roaring, invisible cage of lethal forces. Entering it without protection is less a matter of surviving for minutes than of surviving for fractions of a second. A neutron star forms when a star far more massive than our sun exhausts its nuclear fuel. Its core collapses under gravity with such force that protons and electrons merge into neutrons, creating a sphere barely 20 kilometers across, but with more mass than our sun. The surface gravity here is around 200 billion times that of Earth. You cannot stand on a neutron star, not because of the heat or the radiation, but because the gravitational pull would flatten you to a subatomic smear faster than your nerves could send a signal. But even before you reach that impossibly dense surface, you'd have to pass through its magnetosphere. This magnetosphere is an invisible region dominated by the neutron star's magnetic field, which can be trillions of times stronger than Earth's. To put that in perspective, the strongest magnetic fields we can create in laboratories might reach a few tens of Teslas. A neutron star's magnetosphere, tens of billions of Teslas. At these field strengths, the familiar structure of matter begins to break down. Electrons are forced into tight, elongated orbits along magnetic field lines, transforming atoms into strange, needle-like shapes. If you were anywhere near this environment, your own atoms would feel the pull, molecules in your body twisting and stretching in ways no life form could withstand. Before the field even touches you directly, it affects the space around you. Charged particles trapped in the magnetosphere spiral along the field lines at near-light speeds, emitting beams of high-energy radiation. For many neutron stars, these beams sweep across space like the beams of a lighthouse, producing what we observe as pulsars. If you crossed the path of one of these beams, the blast of gamma rays and X-rays would slice through your body and equipment, ionizing molecules in a spray of secondary particles. These photons don't simply burn, they deposit energy deep within tissues, breaking DNA strands in clusters, overwhelming cellular repair mechanisms instantly. The intensity of the radiation here is beyond anything seen in the solar system. Near Earth, a lethal radiation dose might be a few grays, enough to cause acute radiation sickness and death within weeks. Inside a neutron star's magnetosphere, the dose could be in the range of millions of grays per second, enough to cause complete neural shutdown before you could comprehend the danger. Even shielding meters thick wouldn't be enough. Gamma rays this energetic would punch through with only modest attenuation, creating showers of particles that would destroy electronics as easily as they destroy living cells. The environment is also electrically violent. A neutron star's rapid rotation, often dozens to hundreds of times per second, drags its magnetic field around with it, inducing electric fields so powerful they can rip particles from the surface and accelerate them to ultra-relativistic speeds. These particles slam into anything in their path, with energies far greater than those produced in our most advanced particle accelerators. For a human, there is no resisting this kind of bombardment. Even a fraction of a second of exposure would be enough to break down nervous system function, not by heat, but by direct electrical disruption of the ion channels in your neurons. Approaching a neutron star is not like approaching other celestial hazards, where danger ramps up gradually. Here, the transition from survivable to instantly fatal can happen over a distance of a few hundred kilometers. Well before gravity becomes the main killer, the magnetosphere ensures there is no escape. Your spacecraft's electronics would fail first, overwhelmed by induced currents and radiation damage. Navigation systems would glitch, then die. Communication would be impossible, not because the signal is blocked, but because the equipment sending and receiving it would be fried into silence. Even if you somehow floated in the magnetosphere without colliding with the neutron star itself, the forces would begin to affect you physically in ways that are difficult to imagine. At field strengths of billions of Teslas, quantum electrodynamics predicts that the very vacuum of space becomes polarized, behaving like a strange crystal that bends light in unusual ways. You might see the light from distant stars split into components, their polarization altered, the colors slightly off. But you wouldn't have long to marvel. The same field would distort the orbitals of atoms in your body, altering chemical bonds and rendering organic chemistry, the very basis of life, non-functional. Temperature adds another layer of danger. Newly formed neutron stars, called magnetars if they have especially strong fields, can have surface temperatures of millions of degrees. Even an older, cooler neutron star radiates X-rays simply from the residual heat of its formation. These X-rays would pass through your body as easily as through your spacecraft's hull, delivering energy directly into molecular structures. Unlike the heat of a star's surface, which can be blocked to some extent by shielding, this is heat delivered molecule by molecule, atom by atom, with no external sensation until systems fail. The magnetosphere is also dynamic. Field lines snap and reconnect in violent events similar to solar flares, but on a vastly more energetic scale. These magnetic reconnections can release bursts of radiation and particles in milliseconds, changing the hazard level faster than any reaction time you possess. One moment might be marginally survivable with extreme shielding. The next, the flux of high-energy particles could spike by orders of magnitude, overwhelming all protection instantly. What makes the magnetosphere of a neutron star uniquely terrifying is that it combines multiple instant kill mechanisms into one environment. You cannot hide from the magnetic field. It penetrates everything. You cannot outrun the radiation. It moves at the speed of light. You cannot shield against the particle bombardment. The energies involved are beyond the limits of our materials. And you cannot just stay further away. The scale is small enough that by the time you are close enough to see the neutron star clearly, you are already in the kill zone. From a distance, the neutron star's magnetosphere might look beautiful, a halo of glowing arcs where particles stream along magnetic field lines, beams of light sweeping rhythmically into space. But this beauty, like the bright clouds of Venus, is indifferent to your survival. It is a trap set by physics itself, one that no amount of bravery or skill could overcome. The only safe way to witness it is from light years away, and even then, you're only seeing the parts that escaped without being annihilated. If the outer magnetosphere is already a death sentence, moving deeper into its grip takes you into a realm where physics becomes increasingly alien. The rotation of the neutron star, in some cases over 700 times per second, drags the magnetic field into a distorted shape, winding and twisting it like a taut rope being spun at impossible speeds. These distortions create zones where the field strength changes abruptly, forming corridors of hyper-accelerated particles. Even without touching the neutron star's surface, entering one of these corridors would be like diving into the beamline of a particle accelerator scaled up to planetary size. Here, individual protons can be hurled to energies in excess of 10 to the 15th electron volts, far beyond the reach of Earth's Large Hadron Collider. When they strike the hull of a spacecraft or the tissues of a human body, they initiate particle cascades, spawning showers of pions, muons, and other exotic fragments that can penetrate meters of solid metal. These aren't hits in the cinematic sense. They are silent annihilations of structure, unraveling molecular bonds and transmuting atoms. For a human being, exposure at this level would produce immediate and total loss of cellular function. It would be less a matter of injury and more a matter of erasure. Magnetars, the most extreme type of neutron star, amplify all of this. With magnetic fields up to 10 to the power of 11 Teslas, they exert forces so extreme that even 1,000 kilometers away, the field could distort the electron clouds of atoms in your body, subtly reshaping their geometry. At close range, this becomes catastrophic. Proteins, the machinery of life, would no longer fold correctly, chemical reactions would stall or behave unpredictably, and the complex dance of biochemistry that defines life would grind to a halt. Death here is not caused by heat, pressure, or even direct mechanical violence, but by the quiet dismantling of the laws that make chemistry possible in the first place. The environment also becomes electrically unstable on scales that defy human engineering. The motion of plasma within the magnetosphere induces voltages that can reach trillions of volts. If a conductive object, like a spacecraft, moves through such a field, it can experience massive electric currents, enough to vaporize circuitry and melt structural components. Unlike the gradual wear of micrometeoroid impacts or radiation damage in low Earth orbit, these failures happen instantly. A guidance system, a communications array, a life support pump, all can be destroyed in the same millisecond, with no warning but a final burst of static. For anyone inside, the sensation would be strange and short-lived. Magnetic fields don't directly stimulate human nerves, but the rapid induction of currents in conductive tissues, blood, spinal fluid, even the fluids inside your eyes, could produce electrical shocks from within your own body. Neurons would fire erratically, muscles would spasm, and the fine electrical balance that keeps your heart beating could be disrupted beyond recovery. You wouldn't have time to interpret it as pain. Your brain's capacity to make sense of signals would be drowned in noise. Even if you were in a perfectly sealed and shielded vessel, the neutron star's radiation output would create another hazard: thermal overload from the inside out. Gamma rays and hard X-rays striking shielding material produce high-energy secondary particles and heat deep within the vessel's walls. Unlike normal heating, which can be managed by radiators and cooling loops, this heat is generated inside your protective layers, bypassing most thermal controls. In seconds, the hull could reach temperatures sufficient to compromise structural integrity, cooking the interior long before the outside looks damaged. And the neutron star's rotation adds yet another twist, literally. The intense gravity of the neutron star bends space-time so strongly that light itself is curved around it, producing a distorted view of the surroundings. If you could see in that final moment, you might notice the star's far side appearing above its surface, its beams of radiation sweeping across the distorted horizon in dizzying arcs. This warped view would be the last thing your eyes registered before the environment erased your ability to perceive anything at all. For pulsars, neutron stars whose beams align in just the right way to sweep over you, there is the added danger of rhythmic exposure. The beams deliver bursts of energy at precise intervals, like a cosmic heartbeat. These bursts can be more damaging than continuous radiation because the pauses allow physical systems, including living cells, to partially recover between hits, making them more vulnerable to the next strike. It's a cruel echo of medical radiation therapy, except here the goal isn't treatment, and the doses are billions of times higher. The deeper you go, the more the concept of inside the magnetosphere becomes meaningless. The field lines that shape it are anchored to the neutron star itself, and they extend far into space, linking the star's rotation to the motion of its surroundings. If you cross certain boundaries, such as the light cylinder, where the field lines would have to move faster than light to stay anchored, you enter regions where the plasma dynamics become unstable, chaotic. Magnetic reconnection events here can release more energy in a single moment than the sun emits in a year. Being caught in one would be indistinguishable from being struck by the blast front of a small supernova. Ultimately, the neutron star's magnetosphere is a place where minutes to live is far too generous. For any human, it is a fraction of a second kill zone, where death can come from radiation, from induced electrical currents, from chemical disruption, or from structural failure, often all at once. It's not a place that will ever be made safe, not with shielding, not with distance within its reach. The only survival strategy is never to enter it at all. And yet, like the other deadly places in the universe, it exerts a fascination. Astronomers study neutron stars not just because they are exotic, but because they are perfect laboratories for physics under extreme conditions. They show us what matter can become when squeezed and twisted beyond our imagination, and they hint at the boundaries of the physical laws we rely on. From a safe distance, measured in light years, they are beautiful, jewel-like points that flash with precise regularity, cosmic lighthouses marking the remains of once mighty stars. But step too close, and the magnetosphere will not care who you are, how you arrived, or why you came. It will simply unmake you. The hypersonic winds of HD 189733b, far beyond the warm reach of our own sun, orbiting a star some 60 light-years away, lies HD 189733b, a world that, at first glance, looks like a sapphire adrift in the darkness. Its deep blue hue, captured in delicate detail by space telescopes, suggests calm oceans and clear skies. But the reality is as far from serene as possible. This is a gas giant where the atmosphere is a weapon, where winds roar faster than bullets, and the rain itself is made of glass. It is a place where stepping into the open sky, if you could even find solid ground, would end you almost instantly. This cobalt blue world orbits extremely close to its parent star, so close that its year lasts just over 2 Earth days. Its proximity locks it in a tidal embrace, one side permanently facing the star, the other forever turned toward space. On the day side, temperatures soar above 1,000 degrees Celsius, hot enough to vaporize metals. On the night side, the absence of direct starlight plunges temperatures hundreds of degrees lower. Between these extremes lies the Terminator, the dividing line between eternal day and endless night. And here, the planet's winds become the most dangerous in the galaxy. Driven by the enormous temperature contrast, the atmosphere becomes a global conveyor belt of air, moving at supersonic speeds. But here, supersonic is an understatement. Measurements suggest winds reaching up to 8,700 kilometers per hour, over 7 times the speed of sound on Earth. At those speeds, the air isn't just moving, it's scouring. Any object caught in this flow would be shredded molecule by molecule as the atmosphere whipped it around the planet in mere hours. The winds are not composed of air in the way we know it. This tempestuous planet's atmosphere is thick with silicate particles, microscopic shards of glass suspended high in the clouds. These particles are formed when silicon and oxygen, abundant in the atmosphere, condense at high altitudes. Carried by the winds, they become a constant horizontal sandblasting storm that covers the entire planet. Here, rain doesn't fall straight down. It moves sideways at hypersonic speeds, each grain slicing through anything in its path like a tiny, high-speed blade. Imagine opening your visor to take a breath, not that you could, and being hit not by a gust of wind, but by a river of molten sand moving faster than an assault rifle bullet. The impact force alone would pulverize bone and shred tissue. Your suit, no matter how advanced, would quickly become pitted, weakened, and ultimately breached. The pressure differential and chemical makeup of the atmosphere would finish what the glass rain started, tearing away your last defenses. The light here is strange. The blue color we see from space comes not from oceans, but from the scattering of starlight by the silicate-laden clouds. The star's light is filtered through this haze, giving the sky a dazzling but deceptive glow. For an observer in the upper atmosphere, the horizon would shimmer as if the air itself were liquid crystal. But the beauty masks a constant planet-wide storm, with no calm eye and no pause. The heat on the dayside adds another layer of fatality. At over 1,000 degrees Celsius, the air itself becomes a medium of thermal conduction, capable of cooking any material that lingers too long. Metal components would expand, warp, and melt. Human tissue would vaporize. Even reinforced alloys would only survive minutes before softening. And because the winds are global, there is no refuge on the night side. The scouring storm carries the heat with it, ensuring that even the coldest regions are still catastrophically hostile. The pressure isn't crushing like Venus's, but that's no mercy. The thinness of the upper atmosphere means there's little to slow down the silicate particles. On Earth, raindrops reach terminal velocity in seconds. Here, glass shards propelled by the jet stream keep accelerating until they collide with something, or someone. That something would not survive the impact intact. The storms are relentless because this alien gas giant is locked in a permanent tug-of-war between its blazing dayside and its frigid nightside. Unlike Earth's weather systems, which can break apart and dissipate, the forces here are constant, ensuring the winds never stop. This perpetual circulation means there is no safe window, no quiet season. The storm you face on your first second here is the same one that's been raging for centuries and will rage for centuries more. If you somehow floated above the surface, in a hypothetical balloon perhaps, your view would be stunning. Beneath you, roiling clouds stretch across the globe, their patterns sculpted by the ceaseless winds. Occasional lightning flashes might ignite within the storm, briefly illuminating the glass-laden atmosphere. Each flash would be more than a visual spectacle. It would be a reminder of the massive energy coursing through the air. The lightning would superheat pockets of the atmosphere, altering wind currents in ways that could tear apart anything attempting to hover. For a spacecraft attempting entry, the challenge would begin long before reaching the cloud tops. The silicate particles would sandblast the heat shield, eroding it faster than re-entry through Earth's atmosphere ever could. At hypersonic speeds, even microscopic abrasions can escalate into catastrophic breaches, allowing superheated air to infiltrate and destroy structural integrity from within. And unlike Earth, where entry happens once and then you're clear, here the turbulence is omnipresent. You'd be battered constantly from all sides until you either escaped or succumbed. The violence of this place is not just physical, it's also chemical. The atmosphere is primarily hydrogen and helium, but the presence of silicon compounds and other exotic molecules means that reactions occur at high temperatures that would never happen naturally on Earth. These reactions can create unstable compounds, adding chemical burns and toxic interactions to the list of lethal effects. Breathing here is, of course, impossible, but even through a sealed suit, The atmosphere's chemistry could corrode materials and poison systems. This cobalt blue world is deceptive in the same way Venus is. From a distance, it promises beauty and intrigue, but up close, it is a perfectly tuned machine for destruction. The combination of hypersonic winds, glass rain, and extreme heat means that there is no way to adapt, no technology we currently possess that could make long-term survival possible here. Even a brief visit would be gambling against odds so high they might as well be absolute. Descending deeper into the atmosphere of this tempestuous planet would not bring relief. Only new kinds of danger layered on top of the existing ones. The upper regions, where winds howl sideways at thousands of kilometers per hour, are at least somewhat transparent to starlight. As you move lower, the density of silicate particles increases, thickening the blue haze into a darker, storm-churned twilight. Visibility drops, not because of nightfall, but because the air itself becomes a swirling wall of microscopic glass. Every square centimeter of exposed material is under constant abrasion, polished down to nothing. In a matter of minutes, your visor would be scored into opacity, sensors would be blinded, and external cameras would transmit only static and shadow. Within this mid-layer, the heat becomes an even more insidious killer. Here, the atmosphere is hot enough to melt most metals outright, and the silicate particles, already razor-sharp, can carry that heat into whatever they strike. The effect is like being inside an industrial sandblaster that also happens to be a blast furnace. A spacecraft's thermal protection system would have to fight a battle on two fronts, shedding incoming heat while also resisting the mechanical erosion of high-speed impacts. Eventually, the compromise would come, a microscopic fissure turning into a fatal breach as superheated hydrogen and helium flood into vulnerable spaces. Lightning becomes more common here, generated by the turbulent motion of charged particles within the silicate clouds. Unlike terrestrial lightning, these discharges can stretch for hundreds of kilometers, arcing through the dense atmosphere with a brightness that would overload unprotected optics. The electromagnetic pulses from such strikes would ripple through electronics, knocking out navigation systems, guidance computers, and communication arrays in an instant. For a human occupant, the flash alone could overwhelm any visual protection, searing retinas before the mind could register the strike. Even if you could hover motionless, an impossibility in such a wind, the constant bombardment would erode every surface until structural failure was inevitable. Protective coatings would peel, composite layers would delaminate, and micro cracks in metals would spread under the constant thermal cycling. Temperatures here swing wildly depending on whether a given parcel of air has recently been pulled from the day side or the night side, and these swings can occur in seconds. Such rapid expansion and contraction is brutal on materials, creating a slow-motion destruction that complements the immediate violence of wind and glass. Approaching the planet's lower atmosphere is even more dangerous. Here, the pressure begins to mount, not to Venus-like crushing levels, but enough that gases are compressed into superheated, super-dense fluids. The silicate particles may no longer remain suspended. Instead, they begin to rain more steadily, falling in a slant under the still roaring winds. But by now, the glass is molten, its droplets glowing faintly as they descend. Imagine being in a sideways shower of liquid blades, each droplet hot enough to melt through solid metal. This is not a hazard you can shield against. It is one that erases barriers entirely. The transition from windborne shards to molten glass rain also changes the way the environment attacks you. In the upper layers, the impact trauma and abrasion dominate. Here, thermal penetration takes over. Once a molten droplet strikes a surface, it adheres, spreading its heat into the material before being whipped away by the wind. In seconds, structural materials can be weakened to the point of collapse. A human body caught here would be cooked from the outside in and then sliced apart as the wind carries more molten rain across every exposed surface. Even the planet's deep interior offers no comfort. Like other gas giants, there is no solid surface to stand on, only increasingly dense layers of exotic matter, transitioning from hot hydrogen gas to metallic hydrogen under pressures and temperatures beyond any Earth-based experience. Theoretically, if you could descend far enough, you would encounter a region where the pressure alone would crush you instantly. But in practice, no living thing would survive long enough to make the journey. The upper atmosphere is lethal within seconds. The lower atmosphere is annihilation before you can measure the depth. From an orbital perspective, the most striking feature of this cobalt blue world is its consistency. The storms never die down, the winds never falter, the glass rain never stops. It's a closed-loop system of violence, driven by the unending heat from the star on one side and the cold vacuum of space on the other. The planet has no seasons, no reprieves. It is locked in a permanent weather war with itself. This constancy means that any point in time, anywhere on the planet, is equally deadly. The day you arrive, the storm has already been raging for centuries, and it will continue to rage long after you are gone. Theoretically, if we could somehow extract samples from this world's atmosphere, they would tell a story of alien chemistry and physics unlike anything on Earth. The silicate clouds themselves are a natural laboratory for studying high-temperature condensates, while the winds provide clues about fluid dynamics in extreme environments. But getting those samples would be the hardest part. Any probe we send would need to withstand not only the mechanical and thermal punishment, but also the sheer unpredictability of wind-driven currents. A momentary change in direction or velocity could subject it to stresses far beyond its design limits. And then there's the haunting beauty of it all. From space, the blue is luminous, deep, and deceptively tranquil. The kind of color you might expect from a peaceful tropical sea. But that sea is an illusion, a mask for an atmosphere that tears, shreds, and melts anything unlucky enough to drift inside. It is a reminder that beauty in the universe is not always a sign of safety. Sometimes the most breathtaking worlds are also the most efficient killers. In the end, survival here is not about how tough you are, how fast you can move, or how clever your technology is. It's about not being here in the first place. This alien gas giant is not a challenge to overcome. It is a boundary in nature, a place where the physics of wind, heat, and chemistry combine into something absolutely hostile to life. The only safe way to experience it is through the filtered lens of distant observation, where the blue glow can be admired without feeling the glass rain against your skin. Up close, admiration lasts only as long as it takes for the first shard to strike. Titan's methane lakes under cryogenic skies. In the frigid outer reaches of the Saturnian system, shrouded in a haze of golden smog, drifts a moon that looks deceptively calm from orbit. Titan, Saturn's largest moon, is a world of lakes, rivers, and rain. But not of water. Here, the temperatures plunge so low that methane and ethane behave like water does on Earth, forming seas, shaping coastlines, and falling from the sky as liquid precipitation. It is a place where the air is thick enough to walk through without a pressure suit, but where the very breath you take would suffocate and freeze you in seconds. On the surface, Titan is dim. Its thick, nitrogen-rich atmosphere scatters sunlight into a perpetual amber glow, leaving no sharp shadows and no clear view of the stars above. The light is soft but oppressive, a constant reminder that you are buried beneath hundreds of kilometers of dense haze. Unlike the violent storms of Venus or the glass rain of distant exoplanets, Titan's lethality is quiet, creeping in through chemistry, temperature, and the peculiar properties of its alien liquids. The air itself is mostly nitrogen, with methane making up a few percent. To human lungs, this mix is useless. Oxygen is absent, but that's only the first problem. At Titan's surface temperature of roughly -179 degrees Celsius, any unprotected skin would begin to freeze almost instantly. The moisture in your eyes and lungs would crystallize in moments, making even a single breath fatal. This is not the quick frostbite of an Arctic winter. This is the immediate seizing of biological processes, a lockup of life at the molecular level. Walking here without thermal protection would be like stepping into a cryogenic storage tank. Your breath would form thick clouds in the dense air, but only for a moment before it condensed into frost that clung to your visor or faceplate. Even through protective clothing, the cold would infiltrate, sapping heat at a rate no natural environment on Earth can match. Titan's dense atmosphere conducts heat away more efficiently than a vacuum, and in temperatures this low, every calorie your body produces is stolen almost as soon as it's made. And then there are the lakes. Titan is the only place in the solar system, besides Earth, known to have stable bodies of liquid on its surface. But where Earth's lakes shimmer with water, Titan's are dark, mirror-smooth expanses of liquid methane and ethane. To human eyes, they might appear beautiful in a muted alien way, dark reflections of the orange sky above, their surfaces barely rippling in the calm air. But beauty here is deadly. If you fell in, you would not have time to swim. At these temperatures, contact with the liquid would rob heat from your body so quickly that you would be unconscious in seconds. Within minutes, your tissues would be as rigid as stone. The chemistry of these lakes adds another layer of danger. Methane and ethane are not only cryogenic, but also flammable under the right conditions. Titan's lack of free oxygen makes fires impossible here naturally. But if you brought your own oxidizer, say inside a malfunctioning piece of equipment, even a spark could trigger a brief, violent reaction. The irony is that in this frozen wasteland, combustion is both impossible and explosively dangerous if triggered artificially. Beneath the still surfaces of the lakes lies an alien fluid dynamic. Liquid methane and ethane are far less dense than water, and their viscosity is lower. If you tried to swim in them wearing a protective suit, your buoyancy would be reduced, making you sink more easily than in water. The liquids would also infiltrate any breach in your suit rapidly, chilling you instantly and freezing the inner layers solid. Unlike water, which becomes less dense as it freezes, methane and ethane maintain high density even as solids, meaning ice here would not float. It would sink, dragging anything encased in it toward the lake's floor. The terrain around the lakes is just as dangerous as the lakes themselves. Shores may appear solid, but can be layered with hydrocarbon slush, a mix of ice, organic compounds, and liquid methane that can trap a foot or vehicle wheel in an instant. Moving through such terrain without the ability to lift yourself completely free risks breaking seals in your suit or damaging thermal systems. Once a breach occurs, there is no time to fix it before the cold takes over. The atmosphere itself, while dense, is not benign. Titan's haze is filled with complex organic molecules created when sunlight interacts with methane high above. These molecules slowly settle to the surface, forming a thin layer of dark, tar-like material over much of the landscape. This Tholin's layer absorbs what little sunlight penetrates the haze, contributing to Titan's deep chill. While not directly toxic to touch, these organics can foul equipment, clog filters, and coat sensors, further complicating survival. If you were to travel from the lakes inland, you would find dunes, not of sand, but of dark hydrocarbon grains blown into long, parallel ridges by Titan's slow but steady winds. These dunes stretch for hundreds of kilometers and can be tens of meters high. While the winds on Titan are gentle at the surface due to the dense air, their persistence means they can slowly bury structures, equipment, or vehicles over time. For a stranded explorer, it would be possible to be buried by creeping dunes before rescue arrived, the weight of the frozen hydrocarbons locking you in place. The cold affects more than just biology. Most materials behave differently at cryogenic temperatures. Metals become brittle, plastics shatter, lubricants freeze. On Titan, any moving part in your suit or equipment must be designed to operate in deep cryogenic conditions. A stuck valve or frozen hinge could mean the difference between safety and death. A visor that frosts over from internal moisture could leave you blind in a terrain where navigation is already nearly impossible. And then there is the isolation. Titan's thick atmosphere blocks most views of Saturn, so even the majestic rings are hidden. The sky is the same hazy amber no matter where you look, with no stars visible to orient yourself. Distances are deceptive in the diffuse light. A hill might be much farther away than it appears, and features blend into each other in the haze. Without reliable navigation, wandering away from a safe zone could mean never finding it again. For all these dangers, Titan has an allure unmatched by many other worlds. It is a place where rivers carve valleys, where rain fills lakes, where erosion shapes landscapes, all through the alien medium of liquid hydrocarbons. From orbit, it could almost pass for an Earth-like moon, with familiar hydrological features. But the hydrology here is built on substances that would kill you on contact, under skies that freeze you from the moment you step outside. It is a mirror image of Earth's water cycle, inverted into a form that is both fascinating and deadly. The longer you linger on Titan, the more its dangers begin to layer into something inescapable. The cold here is not just an absence of heat. It is an active, relentless sink that drains energy from everything it touches. In such an environment, survival is not about staying warm. It is about outrunning the loss of warmth for as long as your systems can endure. Even with the most advanced insulation, every second is a negotiation between the heat you can generate and the heat Titan steals from you. The methane lakes are the most visible threat, but they are not the only liquid hazards. Smaller pools and streams of methane-ethane mixtures can form unexpectedly after a rainstorm, filling depressions in the ground. Because Titan's gravity is only about 14% of Earth's, liquid flows more slowly and can pool for longer before evaporating back into the atmosphere. This means you might walk into what appears to be solid terrain, only to have it give way under you, plunging you knee-deep into cryogenic fluid. At negative 179 degrees Celsius, that's enough to freeze through multiple layers of insulation in seconds, locking you in place with ice that doesn't melt without deliberate heating. The rain itself is lethally deceptive. On Earth, a rain shower might be refreshing. Here, methane rain would be nearly silent, falling slowly in the dense atmosphere. The drops would land with a soft patter, but their cold would burn. Even small leaks in a protective layer could allow the liquid to seep in, instantly freezing into an icy crust that stiffens joints, immobilizes fingers, and seals tools into place. Once mobility is lost, so is any chance of escape. In the deeper parts of Titan's seas, like Kraken Mare, the largest, pressure begins to mount. Though the pressure at the surface is similar to that of Earth at sea level, descending even modest depths in liquid methane and ethane increases the load on your body and equipment. While not as crushing as a descent into Earth's deep oceans, the real danger is the cold. At depth, there is no heat from sunlight at all, and the thermal drain is absolute. Any power source you rely on for warmth would burn through its reserves at an accelerated rate, and there's no way to replenish them here. The terrain away from the lakes carries its own threats. The dunes, composed of hydrocarbon granules, shift with time. While they move slowly, their fine particles infiltrate machinery, grinding into bearings and joints. These particles are not inert sand, but complex organics that can become sticky at certain temperatures, welding themselves into moving parts. A rover or lander trapped in a dune might find its wheels or tracks frozen solid, unable to move even when the surrounding material appears loose. One of the more insidious dangers of Titan is psychological. The perpetual twilight, the lack of visible landmarks, and the unchanging amber sky can quickly disorient even the most seasoned explorer. The human brain relies on cues from sunlight and shadow to gauge time and distance. Here, those cues are absent. Hours and days blur together, making it easy to lose track of direction and duration. The dense atmosphere muffles sound, adding to the sense of isolation. Even if a storm were approaching, you wouldn't hear it until it was upon you, and by then, the temperature and chemical effects would already be closing in. For an explorer or a mission, even small failures can cascade into fatal ones. A cracked seal on a storage compartment could allow methane vapor to enter, condensing into frost that jams latches. Batteries exposed to the extreme cold lose capacity rapidly, sometimes delivering only a fraction of their normal power. This can mean life support systems suddenly run short of energy, forcing emergency shutdowns in the middle of operations. Heating systems that work fine on the Moon or Mars can fail here simply because the temperature difference is so vast and the dense air wicks heat away much faster than expected. The thick haze above may seem like a shield against cosmic radiation, and in some respects, it is. Titan is one of the few places in the outer solar system where a human would not be instantly cooked by high-energy particles from space. But this shield is a double-edged sword. It also traps methane-rich vapors and slows their dispersal, making localized pockets of atmosphere chemically unpredictable. Any ignition source introduced in the wrong place could create a fireball, not from oxygen-fed flames, but from exotic combustion reactions involving stored oxidizers and the hydrocarbons all around. Should you attempt to leave Titan's surface, the challenges would not diminish quickly. The atmosphere extends hundreds of kilometers above, and the haze is so thick that climbing into space would mean battling drag far longer than on Earth. Rockets would need to burn fuel longer just to escape, and that fuel, if stored improperly, would be at risk of freezing solid in the tanks. If there is any reprieve to be found, it's in the fact that Titan's gravity is gentle enough to make carrying heavy equipment easier and falling less dangerous. But in an environment where the cold, chemistry, and terrain are all actively working against you, this small mercy means little. Even with reduced gravity, the layers of protective insulation, life support, and energy reserves needed to survive here turn every movement into a slow, deliberate task. The kind where mistakes are punished instantly and harshly. Despite this, Titan remains one of the most compelling destinations for exploration in the solar system. Its methane lakes and rivers are not just hazards. They are windows into a form of chemistry that may resemble the earliest conditions on Earth before life began. Studying them could yield insights into how life might arise in environments utterly unlike our own. But for a human physically present, those same lakes are a death sentence. Their serene surfaces and soft reflections mask an environment that would kill you without spectacle. No raging storms, no towering waves, just the silent, absolute finality of deep cold and alien liquid. To stand on Titan's shore and look out over a methane sea might be one of the most breathtaking sights in the solar system. But you would see it only briefly. The cold would already be clawing through your protection, the air offering nothing to breathe, the strange rain ready to fall. Here, death does not roar or rush. It seeps, freezes, and locks you in place under skies that will never change. And in the stillness of Titan, that might be the most chilling truth of all. The core of a supernova shockwave. There are places in the universe where death is certain but patient. Cold moons, toxic planets, silent vacuum. And then there are places where death is instantaneous, not because the environment is merely inhospitable, but because the energy present is so overwhelming that matter itself is torn apart in an instant. The core of a supernova shockwave belongs to this second category. A region of space where a dying star releases more energy in seconds than our sun will emit in its entire lifetime. A supernova begins quietly, in astronomical terms. A massive star, having fused hydrogen into heavier and heavier elements for millions of years, reaches the point where its core is filled with iron. Unlike lighter elements, iron does not release energy when fused, it absorbs it. With no new energy to counteract the crushing force of gravity, the core collapses in a fraction of a second. In that blink, matter is compressed to densities exceeding that of an atomic nucleus, and the star's outer layers begin to fall inward, smashing into the core at a quarter of the speed of light. What happens next is the shockwave. The rebounding core and the flood of neutrinos released in the collapse push outward with unimaginable force, reversing the infall and hurling the star's outer layers into space. This expanding wall of destruction, the shock front, is what we call the supernova explosion. The temperatures here soar into the billions of degrees, and the density of energy is beyond anything a human-made weapon could approach. If you were anywhere near the core of this shockwave when it formed, you would not have time to register your surroundings. The radiation alone would kill you faster than any nerve impulse could travel from your senses to your brain. Gamma rays of extraordinary energy would flood every molecule of your body, stripping electrons from atoms in a cascade of ionization that would leave nothing resembling biological tissue behind. This is not a burn, not in the way we understand it. It is an instantaneous dismantling of matter on the atomic scale. The shockwave itself is not a gentle pulse of pressure. Traveling at thousands of kilometers per second, it sweeps up anything in its path, compressing it to a fraction of its volume before blasting it apart. For solid matter, ships, planets, asteroids, the force is enough to shatter chemical bonds, vaporize minerals, and fling the resulting plasma into the maelstrom. A human body caught here would simply cease to exist as a coherent object, its atoms scattered and fused into new elements in the roiling chaos. One of the strangest aspects of this environment is the role of neutrinos. In everyday life, trillions of these ghostly particles pass through your body every second without interacting. But in a supernova, the neutrino flux is so intense that their interactions become significant. In the first second of the explosion, the collapsing star releases more than 10 to the power of 58 neutrinos, an almost unfathomable number. This torrent would stream through you with enough collective energy to disrupt nuclei, shattering them into subatomic particles. It is an invisible assault, unstoppable by any shielding known to science. Even if the shockwave's initial blast were somehow avoided, the surrounding environment is utterly hostile. The light from a supernova is so intense that at close range it would vaporize surfaces just by shining on them. In fact, the visible light is only a tiny fraction of the total energy released. Most of it comes in the form of high-energy photons and particles. Within milliseconds, every component of your body would be in a superheated plasma state, indistinguishable from the explosion's own debris. The scale of destruction is difficult to visualize. The shock front expands outward at a significant fraction of light speed, carrying with it temperatures and pressures that can forge new elements, gold, uranium, and many others, from lighter nuclei. These newly forged atoms are blasted into space, seeding future generations of stars and planets. If there's any poetic comfort in such a violent death, it's that your remains, reduced to atoms, would become part of the raw material for new worlds. But that process would not feel merciful. In the chaotic heart of the shockwave, time loses its meaning. The forces involved operate on scales so extreme that human perception cannot keep pace. The distance you could walk in a single step is crossed by the shock front in less than a microsecond. The smallest pause in your thoughts would be enough for the entire event to unfold around you. Even light takes time to traverse the expanding debris, meaning that what you see and what is happening to you may already be out of sync. The pressure inside the shock front is not measured in atmospheres or even in the terms we use for planetary cores. It's measured in billions of pascals, enough to compress normal matter into degenerate states. For an instant, the density of the material passing through, you could rival that of a white dwarf, and the temperatures could strip even the most tightly bound electrons from heavy nuclei. Under such conditions, there is no concept of surviving partially. Either you are entirely outside the blast, or you are entirely part of it. To imagine being here is to imagine standing inside a nuclear explosion scaled up to stellar proportions. And unlike a nuclear bomb, which radiates heat and light in all directions in a relatively small space, a supernova's shockwave is an expanding sphere of annihilation the size of a star, carrying enough energy to sterilize whole star systems. The devastation does not end at the shock front either. Even after the initial passage, the surrounding space remains awash in high-energy radiation for months to years, ensuring that any surviving matter is stripped bare of complexity. From a distance, astronomers see the explosion as a brilliant flash that can outshine an entire galaxy. Up close, there is no brilliance, just the overwhelming, structureless fury of matter unbound. The concept of looking at the core is meaningless because light itself is part of the weapon. There is no vantage point, no safe angle. The whole sphere is deadly, and it is deadly everywhere at once. The violence at the core of a supernova shockwave is not a single moment, but a chain of overlapping catastrophes, each one fatal in its own right. The first is the radiation flash. In less than 1,000th of a second, gamma rays and X-rays pour out in a concentrated burst, carrying more energy than the sun produces over millions of years. Even if you were behind kilometers of rock or metal, the photons would blast through, stripping electrons from atoms, turning solid matter into ionized gas. Inside your body, that energy would shred DNA, vaporize water molecules, and create a storm of secondary radiation from the cascade of interactions. Close on the heels of the radiation comes the particle wind. Protons, neutrons, and heavier nuclei, moving at a significant fraction of light speed, slam into everything ahead of the shockwave. This isn't a gentle breeze. It's a wall of matter so dense and so fast-moving that it behaves more like a fluid than a collection of particles. These high-energy impacts pulverize molecules in crystal lattices, fracturing them into smaller and smaller fragments until the concept of material dissolves into a glowing plasma. The pressure inside the shockwave peaks as the expanding front plows into surrounding space, compressing the interstellar medium into an incandescent shell. For a brief moment, this compression is so extreme that it can squeeze hydrogen atoms together into helium, a kind of flash fusion happening in the wake of destruction. Any human caught in this region wouldn't simply be crushed. Their atoms would be forced into reactions that normally require the heart of a star. As the shockwave expands outward, it carries with it a turbulent mix of temperatures and densities. Some regions are hot enough to trigger nuclear synthesis, creating new elements on the spot. Others are cooler, but still energetic enough to vaporize metals and rocks. The uneven nature of this expansion means that death here is not uniform. It's a patchwork of extremes. You might pass from a region where the radiation is blinding to one where the particle density is overwhelming, only to be struck by both at once a heartbeat later. The neutrino burst, which occurs before most of the visible explosion, is perhaps the most chilling of all. Billions of times more numerous than the photons or particles in the shockwave, neutrinos pass through almost all matter unhindered. Under normal circumstances, they barely interact at all. Trillions pass through your body every second without effect. But here, in the supernova core, their density and energy are so extreme that they begin to interact en masse, slamming into nuclei and breaking them apart. This is a type of damage no shielding can prevent, because shielding works by stopping or deflecting particles. And neutrinos ignore nearly everything in their path. If you were unlucky enough to be in orbit around the star when it exploded, the geometry of the event wouldn't matter. The shockwave is not directional. It expands in all directions at once. Light from the explosion would reach you at the same moment as the lethal radiation. Your ship would be destroyed in the same instant as your body, its materials stripped into a cloud of ions that would be swept away in the turbulent currents of the blast. On slightly larger scales, entire planets are vaporized by this process. Even if a planet is far enough from the star to avoid complete annihilation, its atmosphere will be stripped, its surface baked, and its biosphere obliterated. In some cases, the shockwave can reach other stars, triggering shock compression in the distant gas clouds and starting the process of star formation anew. This is the only kind of legacy a supernova offers, destruction that paves the way for creation elsewhere. The temperatures in the heart of the shockwave defy normal comprehension. At billions of degrees, matter exists only as plasma, not the gentle glow of a neon sign or the confined fire of a fusion reactor, but a violent, chaotic soup where atomic nuclei themselves are under constant bombardment. For any living thing, this is beyond heat. It is complete disassembly at the nuclear level. Bonds are not broken here. They are erased entirely. Even after the initial blast has passed, the region remains dangerous for an extended period. Radioactive isotopes forged in the explosion decay over time, releasing energy and particles into the surrounding space. In a sense, the supernova leaves behind a poison scar on the cosmos, a zone that will remain hostile for thousands to millions of years. Any spacecraft entering too soon would be subjected to lethal radiation long before approaching the remnant's core. The expansion of the shockwave eventually slows, but not before it has traveled light years from its origin. By the time it reaches interstellar speeds low enough to spare planets, those planets have already been sterilized. The energy released is not just destructive, it's transformative. The chemical makeup of the galaxy is forever altered by each supernova as the heavy elements it produces are scattered into the void. Without this process, there would be no gold, no uranium, no iodine, and no life on Earth. From a safe distance, if such a thing exists, the sight of a supernova is breathtaking. A single point of light blossoms into a beacon visible across galaxies. But up close, there is no beauty, only the unstoppable conversion of matter into energy, and the scattering of that energy into everything nearby. The shockwave does not discriminate. Stars, planets, moons, ships, and people are all equal in its path. It is the universe's most absolute form of leveling. In the final tally, the core of a supernova shockwave is not just a place you cannot survive. It is a place where the concept of you is erased in less time than it takes for a thought to form. Your atoms are broken down, forged into new configurations, and scattered into the interstellar medium before your nervous system could register the first hint of danger. It is instantaneous, total, and final. And yet, paradoxically, supernovae are also engines of creation. The same explosion that destroys entire worlds sows the seeds for future ones. The atoms in your bones were forged in such events billions of years ago, scattered by blasts like this one. To die in a supernova shockwave is to return to that cycle, to be taken apart and cast into the cosmos, perhaps one day to be part of something new. But for the individual, for the moment of contact, there is no poetry. Only the absolute violence of a star's final breath, the accretion disk of a quasar. From the depths of the cosmos, certain galaxies blaze with a brilliance so intense they can outshine every star within them combined. At their centers, buried in regions no human eye could ever directly see, lie the engines responsible, quasars. These are not stars, but supermassive black holes consuming matter at such an extraordinary rate that the infalling material forms an accretion disk, hotter and brighter than any stellar surface. To find yourself near the heart of such a disk is to step into one of the deadliest places in the universe, a realm where light itself becomes a weapon, and where every law of survival is obliterated by scale, speed, and radiation. A quasar's accretion disks forms as gas, dust, and even entire stars are drawn toward the black hole by its immense gravity. Instead of falling straight in, the material spirals, colliding and compressing as it circles at a significant fraction of light speed. These collisions convert gravitational energy into heat, pushing the disk's temperatures into the millions of degrees. The inner regions radiate in X-rays and gamma rays, while the outer layers glow in ultraviolet and visible light. To an observer from afar, the disk looks like a radiant halo around a point of infinite darkness. To be close to it is to be bathed in a torrent of high-energy photons capable of sterilizing worlds. The heat alone would be enough to kill instantly. At the temperatures in the inner disk, atoms are stripped bare of their electrons, creating a plasma so hot and dense that it emits lethal radiation in every direction. Standing anywhere near it, even outside the plane of the disk, would mean exposure to radiation doses millions of times higher than a human could survive in a lifetime, delivered in seconds. This radiation doesn't merely burn, it ionizes molecules, turning the chemical basis of life into an unstable wreck almost immediately. But radiation is only the first layer of danger. The disk's rotation speeds are staggering, with inner regions orbiting close to the black hole's event horizon. These speeds create powerful shear forces between neighboring layers of material, generating magnetic fields that twist and reconnect with explosive violence. Each reconnection event releases bursts of energy that can dwarf entire supernovae in localized intensity. If you were in the vicinity, these magnetic eruptions would bombard you with particle storms, so dense and fast-moving they would tear through shielding and matter alike. The light from the accretion disk itself carries momentum, enough, in the most luminous quasars, to physically push matter away at relativistic speeds. This phenomenon, called radiation pressure, is powerful enough to launch winds from the disk's surface, creating streams of gas moving at thousands of kilometers per second. For a human or a spacecraft, being caught in such a wind would mean immediate mechanical destruction, as the force would crush and strip apart anything in its path. The gravitational environment near the disk is equally hostile. While you wouldn't be pulled directly into the black hole unless you cross the event horizon, the gravitational gradient is steep enough to produce severe tidal forces even at what might seem like a safe distance. These forces could distort a spacecraft's structure, flexing it in ways that lead to metal fatigue or outright breakage. For a human, any direct exposure, without the protective envelope of a vessel, would mean spaghettification in moments, as your body's structure failed under uneven pulls. The density of material in the accretion disk means collisions are constant. Every grain of dust, every atom, is on a high-speed path that intersects with others, generating shock waves that ripple through the plasma. These shocks create localized bursts of heat and radiation that spike unpredictably, adding a chaotic element to an already lethal environment. Even if you somehow had shielding that could survive the average conditions, one of these spikes could overwhelm it in milliseconds. One of the most extreme features of a quasar's accretion disk is its sheer size. While the black hole itself might be only a few light hours or light days across, the disk can stretch for light years. This means the luminous region you see from afar is not a point, but a vast, rotating structure radiating more energy than the combined output of hundreds of billions of stars. The scale is so immense that light emitted from one side of the disk could take years to reach the other. yet the entire structure is in constant, violent motion. From the polar regions above and below the disk, quasars can emit relativistic jets, beams of charged particles accelerated to nearly the speed of light. These jets are powered by the twisting magnetic fields in the inner disk and can extend for millions of light years into space. If you were close to where one of these jets emerged, the stream of particles would slice through you instantly, delivering energy so intense it would vaporize matter before any sensation could register. Even without the jets, the radiation environment near the disk is utterly lethal. X-rays, gamma rays, and extreme ultraviolet radiation bathe the surroundings in a continuous flood, ionizing anything that enters. For a spacecraft, this means electronics would fail rapidly as components degraded under the onslaught. For a human, the effects would be immediate: nervous system disruption, catastrophic cellular damage, and thermal overload from the absorption of high-energy photons. If you approach the disk visually, the scene would be both mesmerizing and disorienting. The innermost regions, moving at relativistic speeds, would be warped by gravitational lensing, creating distorted arcs of light around the black hole. The disk's glow would shift in color depending on your angle, with regions moving toward you appearing bluer, and those moving away appearing redder. A Doppler effect taken to the extreme. But the very photons carrying that beauty would be lethal, stripping your body of its structure as they streamed past. The accretion disk is not uniform, it's turbulent. Massive eddies and vortices churn through it, pulling hotter material upward and mixing cooler regions downward. The turbulence means the environment changes from moment to moment. There is no safe zone where conditions stabilize. The entire structure is a living storm of plasma, magnetism, and light, all orbiting a gravitational sink from which there is no escape. To get this close to a quasar is not merely dangerous, it is impossible for any known material to survive. The combined assault of heat, radiation, magnetic disruption, and gravitational stress ensures that no human, no probe, no shield could last more than fractions of a second. Even if you could somehow freeze time, the conditions themselves would be beyond tolerable. A snapshot of destruction, frozen in a frame that no living thing could endure. Moving deeper into the environment of a quasar's accretion disk is not like approaching a simple heat source or storm. It is like entering an overlapping set of lethal environments, each one capable of destroying you on its own. The radiation here is relentless, but its intensity is not static. The brightness of a quasar can vary dramatically over short timescales, hours, days, or even minutes, as dense clumps of matter spiral inward and release sudden bursts of energy. These flares can momentarily increase the local radiation output by orders of magnitude, enough to overwhelm even the most theoretical shielding designs before the flare has fully peaked. The turbulence in the disk adds another unpredictable hazard: shocks and shear zones, where different layers of plasma, moving at different speeds, collide. These zones are like cosmic earthquakes, releasing bursts of kinetic and thermal energy in irregular patterns. For any object in the vicinity, this means conditions can shift from instantly fatal to even more instantly fatal without warning. Navigation becomes meaningless because the hazards are not fixed in place. They are constantly forming, moving, and dissipating in an endless cycle. The inner edge of the disk, closest to the event horizon, is where the violence reaches its peak. Here, matter is moving so fast and is so compressed by gravity that time itself slows relative to the outside universe. From your perspective, the infall into the black hole might seem drawn out, but the rest of the universe would watch you fade away in moments. In reality, you wouldn't last long enough to perceive this time distortion. The heat and radiation in this region are intense enough to strip atomic nuclei of all remaining electrons, turning the plasma into a bare soup of protons and heavier nuclei, the most stripped-down form of matter that still has mass. The gravitational pull here is almost incomprehensible. Even without crossing the event horizon, the gradient in gravity between your head and your feet would be enough to spaghettify you, stretching your body into a thin stream of particles in fractions of a second. In a spacecraft, the same forces would warp the hull, creating stresses that propagate faster than the materials can absorb them, tearing the structure apart from bow to stern. Magnetic fields are another silent killer in the accretion disk's inner regions. The charged plasma moving through the disk generates magnetic fields thousands of times stronger than anything Earth's surface experiences. These fields are constantly reconnecting and snapping, producing explosive events that accelerate particles to near-light speeds. When these particles slam into your body or your ship, they don't just cause burns. They disrupt the very electrical signals that keep systems functioning, whether those systems are biological neurons or computer circuits. A single burst could wipe out your nervous system as cleanly as a magnet wipes a hard drive. Above and below the disk, the energy being generated doesn't just dissipate. It escapes in the form of those relativistic jets, collimated beams of plasma that can stretch far beyond the boundaries of their host galaxy. Even if you avoided the main body of the disk, straying into the path of one of these jets would be catastrophic. The kinetic energy of the particles within them is so immense that even a single gram of material, moving at those speeds, would release energy equivalent to a small nuclear weapon upon impact. In a jet, you would be hit not by a single gram, but by an endless flood. The light from the disk is powerful enough to exert a measurable push on matter, the radiation pressure mentioned earlier. But here it becomes an unrelenting wall. This pressure can blow away gas and dust for light years around. And if you were unlucky enough to be in its path, it would also push against you. While your body wouldn't be shoved aside like a leaf in the wind, the pressure would still transfer momentum to your atoms, creating microscopic forces that contribute to the constant stripping and rearranging of your molecular structure. For a human caught here, the sequence of events leading to death would be difficult to categorize because everything happens at once. Radiation tears apart your cells. Magnetic fields scramble your neural activity. Gravitational tides stretch your body beyond recognition. Thermal energy vaporizes water and soft tissues. The combined assault is so overwhelming that death is almost too slow a word. It is dissolution, the conversion of your matter into the undifferentiated plasma of the disk. Even from a safer vantage point, if such a thing can be called safe, the sheer energy output of the disk poses long-term hazards. High-energy photons and particles stream outward into interstellar space, damaging anything they strike even light years away. Spacecraft operating near an active quasar must navigate the surrounding radiation fields with extreme caution, often taking indirect paths to avoid the most dangerous regions. The irony is that the same radiation that makes quasars lethal is also what makes them visible across the cosmos, serving as beacons to astronomers who will never come close enough to be in danger. The scale of the disk's structure also creates strange optical effects. Gravitational lensing near the black hole can bend light into rings and arcs, distorting the appearance of the disk, so that parts of it seem to be in places they are not. To your eyes, the inner edge might appear above you, while the far side of the disk could seem to wrap around and meet itself. This optical confusion would be your final view before destruction. A warped, spinning panorama of impossible geometry, painted in colors shifted far beyond the range of normal human vision. In the long term, the accretion disk will not last. As the black hole consumes the matter feeding it, the disk will thin, dim, and eventually fade. But this process can take millions of years, and during that time, the quasar remains one of the most efficient killers in the universe. No amount of preparation, no armor, no distance within the active zone can save you once you're in its grasp. To die in a quasar's accretion disk is to become part of the cycle of matter and energy on the largest scales imaginable. Your atoms would swirl inward, heated and accelerated until they cross the event horizon, vanishing from the visible universe forever. In this way, you would join the countless stars, planets, and clouds of gas that have already fed the black hole, contributing, for the briefest of moments, to the light that makes a quasar visible across billions of light years. But in that final moment, there is no grandeur for the one falling in, only the crushing, blinding, overwhelming truth. This is not a place where life can cling to the edges. It is a place where the universe concentrates its power into a storm of heat, light, and gravity so absolute that nothing, not even memory, escapes. The ultra-dense core of a white dwarf merger, far from the calm spiral arms of familiar galaxies, in binary star systems that have outlived their youthful blaze. A quiet but deadly drama sometimes unfolds. Two ancient remnants, white dwarfs, orbit each other in a slow gravitational dance. They are the burned-out cores of stars once like our Sun, compressed into spheres no larger than Earth, but containing more mass than the Sun itself. Their matter is degenerate, electrons packed so tightly that the normal rules of atomic spacing no longer apply. For millions or billions of years, these stellar corpses spiral closer together, losing orbital energy through the emission of gravitational waves. And then, one day, they touch. The moment of contact in a white dwarf merger is one of the most extreme environments in the universe. A sudden ignition of nuclear fury compressed into a space no bigger than a small planet. If the combined mass of the two dwarfs exceeds a critical limit, about 1.4 times the mass of our Sun, known as the Chandrasekhar limit, the merged core can no longer support itself against gravity. This collapse triggers a thermonuclear explosion so vast it can be seen across galaxies, destroying the star in what astronomers call a Type 1a supernova. But even before the explosion, the core of a merging white dwarf pair is a place no human or machine could survive. The densities here are unimaginable. A teaspoon of the material would weigh several tons on Earth. The electrons are squeezed into a degenerate state, while the nuclei form a crystalline lattice of carbon and oxygen. If you could somehow stand on such a surface, ignoring the impossibility of doing so, the gravity would pull you down at hundreds of thousands of times Earth's strength. You would be flattened into a film of atoms before your brain could register the fall. The temperature at the point of merger spikes rapidly. In the final moments before detonation, the friction and compression of the colliding masses heat the core to hundreds of millions of degrees. At these temperatures, carbon fusion begins in earnest, a runaway process, because each fusion event releases enough energy to heat the surrounding material even more, which accelerates further fusion. In less than a second, the reaction front races through the star, converting a large fraction of its mass into heavier elements and releasing an explosion's worth of energy. For anything caught in the core at this moment, death would be beyond instantaneous. The combination of crushing density and blistering temperature would not just kill you, it would dismantle you at the subatomic level. Atomic nuclei themselves are rearranged here, fusing into new configurations. The human concept of a body doesn't survive in such conditions. You would become part of the plasma rushing outward in the detonation. The pressures in the core before the explosion are staggering. Electron degeneracy pressure, the quantum mechanical effect that holds up the star against its own gravity, is at its absolute limit. The tiniest additional compression can cause collapse. This balance is so fine-tuned that even a slight perturbation from the merger is enough to push the system over the edge. At that point, gravity wins. The star's outer layers begin to fall inward, compressing the core even more and sending temperatures skyrocketing. Radiation is another killer here, and it arrives well before the blast wave. In the moments before detonation, the intense heat of the merging dwarfs bathes the region in a flood of gamma rays and X-rays. These photons are so energetic that they pass through ordinary matter with ease, ionizing everything they touch. Any molecule, biological or otherwise, would be reduced to a chaotic spray of charged particles, with no chance of reassembly. The environment is also electrically violent. The merger distorts the white dwarf's magnetic fields, twisting them together until they reconnect explosively. This process accelerates particles to near-light speeds, creating localized storms of radiation and high-energy plasma. For a spacecraft approaching to observe, these storms would fry electronics, overwhelm sensors, and induce lethal electrical currents in any conductive material, including the human body. The scale of the danger grows as the two stars spiral in. In the final minutes, tidal forces stretch and distort each dwarf, tearing streams of degenerate matter from one and feeding them onto the other in a process called mass transfer. This material doesn't flow gently. It slams into the companion at thousands of kilometers per second, creating shock fronts that heat the impact zones to extraordinary temperatures. Standing in the path of such a flow would be like facing a river of molten metal moving faster than a bullet. Except that here, the metal is nuclear density carbon-oxygen plasma, and the impact would vaporize anything instantly. At the very center, the merged core is a trap with no escape. The density is so high that even light takes longer to emerge than it would in open space, scattering countless times before reaching the surface. Inside, pressure waves from the collision bounce and interact, creating regions of even higher compression. These are the seeds of the detonation, the points where fusion ignites and begins to run away. If you were somehow inside this environment, a thought experiment beyond reason, you would be part of the ignition fuel itself, your atoms indistinguishable from the rest of the plasma that will soon be hurled outward. From a purely observational perspective, the lead up to the explosion is silent and hidden. There is no dramatic visual change, no warning flare. Only the slow, inevitable tightening of the orbit as gravitational waves carry away energy. And then, in less than a second, the environment transitions from extreme to apocalyptic. The detonation begins, and everything within the star's radius is converted into expanding plasma, moving at thousands of kilometers per second. For an external observer, unlucky enough to be nearby, the first sign would be the radiation flash. Even before the shockwave of material arrived, the gamma ray burst from the explosion would deliver a fatal dose at extraordinary distances. Closer in, the blast itself would be a wall of incandescent matter, hotter than the core of any normal star, tearing apart everything in its path. There is no possibility of outrunning it. The velocities involved are simply too high. The aftermath is no less dangerous. The explosion leaves behind a cloud of radioactive debris, glowing with the decay of unstable isotopes forged in the blast. This radiation remains intense for months, ensuring that the surrounding space is uninhabitable long after the shockwave has passed. The expanding remnant continues to emit high-energy photons for centuries, marking the site of the catastrophe as a place where no living thing could ever return. The moment the detonation begins inside the merged white dwarf core, there is no pause, no escalation you could react to. The chain reaction is instantaneous. Carbon fusion sweeps outward in a burning front that moves at a significant fraction of the speed of light, converting the degenerate matter into heavier elements in microseconds. This is not like the core of a living star, where fusion occurs in a stable balance for millions of years. Here, the fuel is consumed in a single, all-encompassing flash, and the energy release is beyond comprehension. In the inner regions, temperatures climb into the billions of degrees. At such extremes, not only are carbon and oxygen nuclei fused into silicon, nickel, and iron, but the resulting nuclei are themselves excited into unstable states. Many of these decay almost immediately, producing a blizzard of gamma rays. The photon density becomes so high that radiation pressure alone is enough to help drive the expanding shockwave outward. That radiation front is the first thing to hit anything in its path, long before the physical debris arrives, and it carries enough energy to ionize and vaporize matter instantly. If you were anywhere inside the expanding layers, there would be no sensation of heat in the human sense. Heat is the motion of particles, but here, the motion is so violent and so energetic that temperature is almost a meaningless word. Your atoms, along with everything else nearby, would be accelerated outward in the shock, stripped of electrons, and hurled into space as part of a glowing shell of plasma. You wouldn't feel yourself burning. You would already be part of the fire. For an observer outside, but close, the next danger after the radiation flash is the arrival of the ejecta, the physical matter of the star itself, now expanding at thousands to tens of thousands of kilometers per second. This ejecta is not a smooth, uniform shell. It is a chaotic, turbulent storm of clumps and filaments, each carrying immense kinetic energy. A single cubic centimeter of this material, moving at those speeds, would have the destructive force of a large bomb. Entire spacecraft would be shredded by the impacts before they could attempt evasive maneuvers. The environment around the blast becomes saturated with high-energy particles. Protons, alpha particles, and heavier nuclei stream outward, each capable of causing catastrophic damage to both biological tissue and electronic systems. Unlike the steady solar wind we know from our sun, this particle storm is a one-time, overwhelming flood. Its density so high that any shielding would be eroded almost instantly. Even at a distance of light hours, the particle radiation could be lethal. Magnetic fields also erupt violently during the detonation. The two white dwarfs' magnetic fields, twisted and compressed during the merger, are suddenly forced outward by the explosion, creating shockwaves in the surrounding plasma. These magnetic disturbances accelerate charged particles to ultra-relativistic speeds, adding even more radiation to the already lethal environment. Space within light days of the blast becomes an electrically chaotic maelstrom, unpredictable and uncontrollable. In the first seconds after the merger's final collapse, the expanding debris shell grows to thousands of kilometers across. In minutes, it's the size of a planet's orbit. The density drops rapidly, but the radiation remains intense. At this stage, the blast is already visible from across the galaxy, shining brighter than the combined light of billions of normal stars. For any nearby planetary system, this marks the end. Atmospheres stripped, surfaces scorched, biospheres annihilated. Inside the debris, the newly forged heavy elements begin their slow journey outward. The explosion has created vast amounts of nickel-56, a radioactive isotope whose decay into cobalt-56 and then into stable iron-56 releases energy that keeps the remnant glowing for weeks to months. This is why a Type 1a supernova fades gradually rather than disappearing immediately after the blast. But during that glowing period, the surrounding space remains bathed in lethal radiation. The white dwarf merger is also a gravitational event. In the seconds before detonation, the tightening orbit emits a final, intense burst of gravitational waves, ripples in space-time that spread across the cosmos at light speed. While harmless to humans directly, these waves are a calling card to observatories, alerting them to the impending catastrophe. By the time the electromagnetic flash arrives, the gravitational message has already been received, though nothing in the universe could respond in time to avoid the blast. For a human caught anywhere near the ultra-dense core during the moment of ignition, there is no sequence of steps to death, no before and after. The conditions are so extreme that all processes occur simultaneously. Radiation burns, mechanical disintegration, and nuclear-level reassembly of your matter into new elements. You become part of the explosion's chemistry in less time than it takes for a nerve to send a signal to your brain. Even the remnants of the blast are hostile. The expanding supernova remnant continues to emit shockwaves as it plows into the interstellar medium, compressing and heating gas clouds in its path. These secondary shocks can trigger star formation far away, but they also create regions of high-energy particle acceleration, producing cosmic rays that can travel for millions of years before colliding with something. For any life form in their path, these cosmic rays are long-range messengers of the original cataclysm, capable of causing genetic damage and atmospheric changes even far from the explosion itself. From a cosmic perspective, white dwarf mergers are vital. They are one of the universe's primary sources of heavy elements like iron, nickel, and cobalt. Every planet, every meteorite, and every living thing containing these elements owes them to such catastrophic events. But this poetic connection is small comfort to anything caught in the act. To be present at the core of a white dwarf merger is to experience the end of all physical identity, to be converted into raw material for the next generation of stars and planets. There is no surviving such a place, no mitigating the risk, no getting clear in time. The only safety lies in distance, light years of it. And even then, the light from the blast will reach you eventually, carrying with it the story of two dead stars whose final act was a single, universe-shaking flash. If you're close enough to witness it with the naked eye, you're already too close to be safe. In the end, the ultra-dense core of a white dwarf merger is not just another deadly location in the universe. It is the absolute edge of survivability, the point where matter itself is pushed past its limits and rebuilt in the crucible of a thermonuclear fire. Here, the difference between existence and non-existence is measured in fractions of a second, and the only trace left behind is the glow of atoms that will drift, cold and silent, until gravity calls them into a new form billions of years from now. I hope you enjoyed this journey through the deadliest corners of the universe. If you're still awake, you'll find another adventure right here on the screen, ready to take you even deeper into the cosmos. Until next time, sleep well, and keep wondering.